Okay, so let's go ahead and look at these examples. I have cosine of some stuff. And so I'm going to set that u equal to the inside of the cosine function. Its derivative is just a constant. The constant's not there, so I'm going to isolate the dx by multiplying by the reciprocal. And so that 2 over pi du is taking the place of this dx, and then I just have cosine of u. You integrate, substitute back in. Let's look at the next one. Now, in this case, I don't necessarily have like something to a power or something inside of a sine or a cosine, but I do have that the top is a derivative of the bottom or a constant multiple of the derivative of the bottom. When you see that, that's going to scream ln to you, because if you set the u equal to the denominator, take its derivative, I'm looking for z squared dz. So I divide by 1/3 or multiply by 1/3, sorry, divide by 3, to isolate the z squared dz. So the 1/3 du is taking the place of the z squared dz. And then the z cubed plus 1, which is my u, is in the denominator. And what's the antiderivative of 1 over u? It's the ln of the absolute value of u. And then I just substitute back in what the u is. So that is a pattern you're going to see often. In fact, in the next several problems, they're all using that same idea where the denominator, its derivative, is a multiple of the numerator. And so that is what we're going to set the u equal to. Okay. You might have been tempted to set the u equal here to just cosine because the cosine is squared. And it's not a bad thing to test it out. But when you do the du, you get negative sine x dx, and that's not what we have in the numerator or the rest of the integrand. Sine of 2x is not the same as negative sine of x, right? So it's okay to try it, but then that doesn't, whoops, that doesn't work. Okay? So I tried again, and this time I tried with the entire denominator. I need the chain rule to take this derivative, so it's 2 cosine x times negative sine x. I move the negative to the other side, and so I have 2 cosine x sine x. You'll notice up here I have sine of 2x. Well, remember your trig identities? Guess what sine of 2x is equal to? 2 cosine x sine x. This is why you have to know those identities, at least some of them, the double angles. Sine of 2x comes up a lot, because you might get stuck here thinking, well, there's nothing I can do, but you use the identity and it works out perfectly. So the sine of 2x dx is taken care of by the negative du. And then once again, if the u is just 1 plus cosine squared, it's just 1 over u. And so I have a ln of the absolute value of that and substitute in again. It's going to look very similar for number 4. I rewrote the tangent as sine over cosine. And again, these are both derivatives of each other. But if I set u equal to sine, then my du is cosine x. And that's not what you have here. You have 1 over cosine x. Cosine in the numerator and cosine in the denominator are not the same function, right? So you can't do this, and that's because cosine is in the denominator, not the numerator in your original integrand. So set your u equal to the denominator, because then when you take its derivative, this sine x is in the numerator. So you can solve for sine x dx. Again, the negative du will substitute in. You're left with the 1 over u, and you integrate. Now, remember, one of the properties of logs is when you have a negative or a number here, it can bump up as a power to the thing you're taking the log of. Well, what's cosine to the negative 1? What's the reciprocal of cosine? It's secant. So you will see this a lot in 193, Calc 2. And you might even just memorize it as a formula because you will see the integral of tangent so many times that you might just remember that and not have to go through that process every time. Okay, last example here. You'll notice that we have an inside function. And so if we set u equal to x minus 1, when we du, we get just dx. And we still have this x floating out front that wasn't taken care of by this du dx process. So far, I can do the square root of u and du, but I need to figure out how to get rid of this x. I can't just put it out front because it's a variable. We're integrating. So instead, when you have this situation where the u and the x are the same power, you can solve this u equals x minus 1 for x and substitute that in. How does that help me? What's the difference between what we started with and what we have here? How are these algebraically different? So here, I can't really move this x into the square root. And so there's nothing, I can't simplify this at all. But here, I can distribute this u to the 1/2. I can multiply to get u to the 3/2 plus u to the 1/2. And now I can do the antiderivative term by term. So the difference is when you have multiple terms under the square root, you're stuck. But if you have only one, you can distribute and get yourself out of that situation. So it's not common, but it does happen. So I'm just substituting back in. Okay. Definite integrals. So when you go to do definite integrals, you have to deal with the limits of integration as well. So you have two options. I strongly recommend you do the first option. In fact, I almost don't even want to show you the second option because then what happens is people put both options together and it doesn't work. And especially your 193 teacher is going to start taking off points. So the first, you have to address, everything else is the same except you have limits of integration. So what I suggest you do is you change the limits of integration from x to u by basically just plugging them in. If you do this option, you never need to change the problem back to x. So you complete the entire process in terms of u. Let's do an example. Okay, so we're going to do the integral from 0 to 4 of the square root of 2x plus 1 dx. So it looks like a good candidate for my u would be that 2x plus 1. My du would give me 2 dx. I don't need the 2, so I'm going to move that over. So starting my process of substitution, I'm going to have 1/2 du to account for my dx. I'm going to have the square root of u, or u to the 1/2. But now I need to address the 0 and the 4. So this is my guide. U equals 2x plus 1. So if x equals 0, then u is 2 times 0 plus 1. I'm just plugging it in. And if x equals 4, then u is 2 times 4 plus 1. So my new limits of integration, my u limits of integration, are 1 and 9. And so what we've done now is we've just completed the whole thing over to u, and you can finish the problem this way. You do not need to convert back. because you have converted your limits for you. So we have 1/3 times 9 to the 3 halves minus 1/3 times 1 to the 3 halves. Remember, to the 3 halves power means take the square root and then cube it. So that would be 27 and 1. So 1/3 times 27 minus 1, or 26/3. Like I said, I strongly, strongly, strongly recommend that you do it this way. The other option, which I told you I didn't really want to tell you about, I'm going to take the same problem. We already did all the work, so I'm just going to kind of copy that down here. We did the du, basically we got 1/2, right? Okay. So if you, for some reason, don't want to plug in the 0 and 4 and just make your life easy, and you want to convert everything back to x, you cannot put 0 and 4 here. Those are x's, not u's. So you have to leave this blank. And so usually what I do is I kind of make an arrow instead of an equals, because technically they're not equal, because one's a definite and one's an indefinite. So you're going to keep doing this, right? And then when you get back to the x, then you can go ahead and put your 0 and your 4 back in and plug them in, and you'll get the same number, right? And once again, it's not really an equals there, because I'm turning an indefinite into a definite. It doesn't go well. What ends up happening for a lot of people is they put the 0 and the 4 here, and then maybe they plug them in there. I strongly suggest you just stick with the first option. Okay, so don't combine these. Don't put the 0 and 4 here, and then put the 0 and 4 here, and then leave them on here, because it's just mathematically incorrect. All right, last but not least, you can also make your life a little bit easier when you're doing integration by using symmetry. So even functions are symmetric about the y-axis, okay? And when you're integrating an even function over an interval that is mirrored, same distance on the left and the right, you can use symmetry to make it easier. So let me just give you an example. Let's say we were going to integrate x to the 4th plus 1, which looks, it's kind of like a parabola, although it's a little flatter at the bottom. From, and this is not drawn all that accurately, -2 to 2. Now, even though you can't really tell from my picture, this first region and this second region are the same. They're equal to each other, because this function is symmetric about the y-axis, and you're going the same distance on the left and the right. So actually, you could rewrite this. You could just double region number 2. I won't finish doing the whole area. I think that part would be the easy part. But why would this be easier than this? I guess maybe if I did keep going. Oopsies. That's a funny too. Right, what happens? I have x to the 5th over 5 plus x. Why is this easier than this? Because 0 is a very nice number to plug in. And so it just makes your ease of calculation that much simpler. Okay. Finally, if you have an odd function, odd functions are symmetric about the origin. So again, if you're thinking I have sine x here, Wow, that was a beautiful picture. Okay. This region is the same as this region. And what happens if I'm going from negative pi over 2 to pi over 2? This region is the same as this region. One's above, one's below. What does that mean? This integral is 0.